Alright. So, all of the equations. Okay, let's go through every single equation.
First one, Coulomb's law.
First one's Coulomb's law. Okay, I think we know that one.
But the second one isn't on the...
F equals, what is it? Absolute value of Q1, Q2 over R squared.
Times
K, yeah, which is K is equal to 1 over 4 pi epsilon naught. So this is the interaction between two charges.
Which is equal to like 9 times 10 to the 9 at the...
Yeah, no, but that's on your number sheet. If you guys don't already know, you should probably remember that like repel and then opposite attract.
Yes, opposites
Oh,
attract.
hell yeah.
Okay, so anything you think you might need to remember, write down on your note sheet.
Also, another one that is taught here is polarization and charging by rubbing stuff, and then charging by the other one.
Yeah.
Connected to a ground. What's that called?
I don't know.
Charging by...
Static electricity?
What's it called when you ground something and then you put it there so that it attracts all the of one type and then all the rest of them exit, and then when you pull it away, you take off the ground and then you pull it away and then it's charged?
That would be well, that's what what are they, like the Gregg generator? Nah, it's like the thing that you do in physics 1, where you put your hand on it and then it puts a static charge in you.
Oh no, I think that actually might be the same.
Yeah. It's called like Gregg generator or something weird.
Alright, so next we have F equals QE. So force times electric field is equal to, electric field times charge equal to force. And we have Q times V.
Sorry, it's called charging by induction.
Charging by induction. Okay, everyone know these? These are important.
V equals QV.
U equals QV.
Oh, well,
Yep.
oh yeah, I know.
We know Gauss's law.
Wait. Aren't there certain conditions for when the force is equal to when the electric field is equal to the whatever divided by the force divided by the charge? Is there specific conditions for that?
That's just for like a point charge, I guess. A uniform electric field.
Okay, and then if there's multiple point charges, does that still hold out?
Well, I guess you can just add them all together.
Oh yeah, because it's the sum of the forces.
Okay, then we have, sum of electric field is just equal to electric field. Sum of voltage is just equal to voltage.
Whoa.
Because of superposition. Sum of potential energy is equal to potential energy. Okay, there you go. So if you have multiple electric fields, you just add the vectors together.
Oh. If you have multiple magnetic fields, can you add the vectors together?
Yeah, of course.
Okay.
Superposition.
What does that mean, superposition? I I know what it means quantum-wise, but
Well, if you have a person pointing on you from the back and a person pointing from the front, you just add the forces together. Same for electric field and magnetic field, which are just sort of forces.
just a force.
Yeah.
That's nuts.
Mm-hmm. So then we have.
And then flux is move up one equation.
Yeah.
That's flux, right?
This is electric flux. And we have a plate. We know that for a single plate, we have it's uniform on the top and bottom, and the electric field is equal to the charge density over to epsilon naught. For a capacitor, it's not actually on the equation sheet. Sort of is.
Kind of is.
Is. capacitor with 2 plates, we have E vector is equal to sigma over just epsilon, because there's 2 of them, and it goes. The electric field will go towards the negative charges.
Are you allowed to tear your equation sheet out of your test?
No.
Really?
Yeah. Electric field always points towards negative. Electric potential voltage will decrease or increase as it gets closer to a negative charge. I think it will decrease.
It'll decrease. No, yeah, it'll decrease.
Yeah.
The potential wants to decrease. So
Right, the potential wants to decrease.
closer
Exactly.
to negative.
Decrease towards minus. Because remember, the potential energy wants to decrease, and if you have a positive test charge, then V also wants to decrease. What else we got? Charge is conserved. Sum Q is equal to Q. Raja, what happens with an insulated material versus a conducting material?
The permittivity is different. It's not that permittivity for space, but and also
No, that's not what I mean. Property of charges in a conductor.
Charges move around in a conductor.
Yeah, exactly. Charges move in conductor.
And extra charges always move to the outside
Yeah. Extra
and are equally distributed.
moves to surface distributed equally. You guys remember the symbols for charge distributions? Lambda is equal to dq dl, sigma equals dq dA, rho is equal to dq dV. You guys are taking notes on things you want to take notes on? You guys remember all this?
I don't think we need to know that.
Electric field points towards negative is helpful. Electric potential decrease towards negative.
What do you mean points towards net? Okay, yes, yeah.
The vector.
Just like a positive point charge.
It's easy to forget and go along with it. It's important concepts we test on a lot of MCQs.
It is, yeah.
Alright, then we have kappa times epsilon naught is equal to epsilon. That's the permittivity, the relative permittivity.
Is it the dielectric constant?
That's a relative dielectric constant. Yeah.
Where's that? Where's that on the? Is that not on the equation sheet?
I don't think it is. Might be.
Not really important.
Dielectric constant. We have.
I don't think that comes up.
It kind of does.
It kind of does.
What do you mean?
Derivative of voltage dx, negative of that is equal to electric field.
X.
That's nice.
What? Like EX,
dv dx is equal to E.
X.
No. V is equal to negative dx for uniform.
Oh.
Otherwise, we have V is equal to negative integral of E dot ds or x.
Wait, they don't explain what mu means on the. Or maybe they're just saying it's a constant.
And potential energy is also equal to force ds. So du dx, negative of that is equal to force.
S is distance, right?
Yeah, s is just like x. Yeah, this is the position vector. Conductors touch. What happens?
Charge transfer.
Yeah, but to do what? Equalize the charge on both of them?
Yeah.
No. Equalize voltage.
Equalize voltage.
Just set them equal to each other. And then solve. A dot B is equal to what? over taking the magnitude. A, B,
Cosine.
cosine theta. Magnitude of A cross B.
That'd be AB sine theta.
AB sine theta.
Like,
I mean, that's for like the E dot A cosine theta. For the integral of the EDA, is just EA is equal to AB EA cosine theta.
Yeah.
Because that'll come up on at least one or two questions.
So this is also for any, if it's uniform, right? We just get EA equals Q over epsilon naught. So then we have E equals Q over E epsilon naught A. If we have any uniform thing while we're going on, you can usually throw that equation out and it works. Echo. Okay. That's what?
EA is constant. Oh, okay, yeah.
Yep. How far are we on the equation sheet?
Oh yeah, the conductor's touching doesn't make the same charge, it just makes the same voltage.
Yeah.
Yeah.
You didn't write that, you just said V.
Oh, I got you.
It's just
Equal-
important. It's just
equalize
yeah, no. It's just important to note that the
Right.
it's not the charge. It's the voltage.
If you want it, I'm ready.
See, if you have a big ball, if you have a big ball and a small ball,
Yeah.
You think I can land it?
You're close.
if you have a big ball and a small ball, the big ball will have more charge.
Right, because
If you
you
touch
sum
it.
up the charges, but then you equalize the voltages. And the charge can distribute how it wants to.
And voltage of charge in a big ball, there's gonna be more charge per voltage. Yeah, I think about balls in that. Because
For capacitors,
a lot of their stuff is based on circles and balls that you touch together between a wire, or you just touch together directly.
Balls that touch together.
okay, so for capacitors we know that Q equals CV. Okay. And if we plug in this equation for a capacitor, so the electric field is equal to sigma time divided by epsilon. E
Oh yeah, voltage is equal to charge over
over
resistance.
epsilon, multiply both sides by A. Now we have Q. So now we have E times EA equals Q. E times epsilon A. And we have capacitance is equal to electric field times A times V. What the heck? E times A times epsilon over V. What am I getting at here? Yeah, we just knew E. Wait. God damn it. E is equal to
E is equal to the dielectric.
Q. Right.
Cathode,
This is
cathode.
electric Q. Wait, oh man, I just oh my god. Just got nowhere.
Bro. Oh yeah. C is Q. That's for an ideal capacitor.
Yeah, for a parallel plate capacitor. Right, so we're supposed to do integral of both sides with respect to x. So we have EX epsilon A equals CV x. We call this D because it's the distance across them. So E times D is just equal to voltage. Cancel out the voltages, and now we have capacitance is equal to K E A over D, and that's what's on the equation. Yeah, epsilon. Sorry. Alright, so remember this one. And then remember Q equals CV. And C that's just the same thing as that thing. Capacitors in parallel. Resistors in parallel, resistors in series. Russia?
Oh, I got you.
Tangent bands, brain run.
I'm looking down.
Oh,
at
okay,
that.
fair enough, fair
Yeah.
I'm
Parallel.
just kidding.
For parallel, I mean, it's just like making a bigger parallel capacitor. I mean, parallel plate capacitor, so it's just add them up.
Add them up, exactly.
And then for the other one, it's 1 over the sum of 1 over these.
Yeah.
And then-
Our parallel is the opposite.
And then parallel resistor is the opposite. And then parallel series, what? Resistors in series. It's like making a bigger resistor, longer resistor.
Yeah, exactly.
I know that.
That's good, that's good. I taught you that like a year ago. Don't forget I equals dq dt.
Your
Current is
V equals IR.
V equals IR, that was important for closed loops. And then sum of voltage is equal to electromotive force, or just voltage. Sum of I in minus I out is always going to be 0. That's at a junction, right? The current will always come out the same amount as it comes in.
P equals IV also for the lost
P
power to
equals
the
IV.
resistor.
Or I squared R, or V squared over R. Energy is equal to integral of power dt, and d power dt is equal to, d energy dt is equal to power.
It's the power lost over a resistor and stuff, right?
Yeah, right. So power, that energy is just being dissipated always. All this potential energy is going nowhere, dissipated into heat. Otherwise, the power would be going nowhere. We have potential energy of a capacitor is equal to 1/2 CV squared. Potential energy of an inductor, actually we'll do that later.
Did you already write C equals Q over, or V equals Q over C?
Q equals to V.
Okay.
Great. What else do I have on my notes here? Okay, right.
what voltage is the background? Not so good.
I don't know. So current is equal to current carriers times charge per carrier times the hell?
Number of
Okay.
charge carriers per unit volume.
I don't even know how it is. Where's the equation on the sheet? I equals, it says it somewhere. Can you guys find the charge carrier?
Yeah, it says I equals capital N times
Oh, there.
the
EVDN.
constant.
Right. So amount of electrons times the electron charge times the velocity of electrons times the cross-sectional area. N is apparently like number of charge carriers per volume. Okay.
Yeah. Big ol' N.
So this is kind of like a row almost. No, it's number per volume, not charge per volume. Right, so this whole thing is row. Times cross-sectional area times velocity of each one.
So, oh yeah. So N times Q there is rho.
Conventional current is the opposite of electron flow. Okay. Resistance equals resistivity, which is also a rho, times length divided by area. Wires have no resistance.
In this.
What?
Magical physics.
In the magic physics, yeah. Ideal physics.
So they have like they either have infinite area or zero resistance.
Okay, here's one you guys might not know. Ammeter should be placed where? In series or in parallel with the circuit?
Series.
Series. What about voltmeter?
Same.
Parallel.
Huh?
To measure the potential difference across one.
Oh, because the ammeter measures.
Can't you just put it on one side of a battery and the other side of the battery and it's still 10 or 9?
A voltmeter?
See your point. But that measures the potential across the battery. You're trying to measure the potential in parts of a circuit.
Oh, yeah. Well,
That is in parallel what we just described.
okay, yeah, no. I see. Yeah, I get exactly what you're saying.
Yeah.
Ammeter series? You put
If
it
you
in
put
series.
it across something, you couldn't measure any current.
Yeah.
You'd be measuring the current of the ammeter itself.
Oh, you're
That'd
right.
be a separate loop.
Yeah.
So yeah.
So it has to be a part of the thing.
Yeah, so don't mess
And
with
then
it.
also,
It's gonna,
in
these are common questions.
ideal, neither of them have resistance, but an actual.
Right, no. An ammeter ideally has no resistance, and a voltmeter ideally
Also,
has
ideally has no resistance.
ideally has infinite resistance.
Okay, sorry, yeah, you're right.
Oh, so
The current one.
Right.
So wait, we treat air as if it has infinite resistance, right?
yeah. And then we just have electrons flying.
It's also supposed to be insulator.
Air is supposed to be insulated.
Oh, I thought you said hair.
No, air.
Hair's an insulator.
Okay.
Here's a
We're erasing this
Yeah,
board.
here's a conductor.
Not
That's
a
how
good
it.
one.
That's how you go.
How many notes have you guys taken? A lot or a little?
Actually,
Zero.
a lot.
Actually, I took like 3.
I took quite a few on it.
I said E equals IR.
Hey, I'm.
If you make
That's-
little pointers on your
okay,
equation sheet, it helps you-
that's like the entirety of the first 3 units.
Yeah. Well, but you have to like know the things before you can just like lay out these
Unit
equations.
4 and Unit 5.
How do we do?
Unit 5's not super
Can we
useful,
go
it's just
through the
Maxwell.
FRQs once you're done with the?
Maybe. I mean, maybe you could do it at home.
Yeah, I might head home.
I need to really focus too much on shit. Yeah, I was gonna go through FAQ last week. I know I didn't come. Those guys can. Okay, so RC circuit we have what's the time constant of an RC circuit? Nathan, what's the time constant of an RC circuit?
Torque? It's like the torque symbol.
Torque. Yeah, well, what's the value? It's probably like
Well, I was just saying it's like the same symbol as torque. I don't know what the actual one
it's RC.
Oh!
Uh,
I remember I saw a problem.
and remember, you start the derivation with E minus or epsilon minus I R minus Q over C equals 0.
Yeah, isn't that tau though?
This is Kirchhoff's. Yeah.
Tau is equal to RC. Oh wait, yeah, no, this is later. Right? This is Unit 4.
No, this is unit 2 still.
Unit 2 or Unit 3?
Unit 2. My unit 2, which is like the unit on these.
Yeah. Because this is circuit, this part of circuits.
The time constant equation is.
So this will represent the charge that fills up in a capacitor.
Yeah.
Time constant 62.2%, or 1 minus e to the negative 1. 0.632. So it's the amount that the Q fills up, it's also the amount that the voltage fills up, but the current is the derivative. Remember, current is the derivative of Q. If you make sure you have that when you're doing your equation. Ferromagnets, or no, let's not get to magnet stuff yet. Are we done with this? You guys need practice on LR equations, or I mean RC circuits. You should probably go watch that lecture again. Come on, man. Yeah, doing something. Okay, general time constant equation. Change is equal to change goal. Wait. Times max. Oh wait, that's what that. Okay, this is change goals max minus initial. And this is current minus a current amount minus initial, not current like electric current, but like current time. Times 1 minus e to the negative t over tau.
Oh, that's for the total something inside something as a function.
Yeah.
This is RC circuits.
RC circuits and LR circuits have like the same properties.
What are RC circuits?
A resistor and a capacitor.
Oh.
And then what's an LR?
Inductor and a resistor.
Oh yeah, I remember.
Oh, they don't have inductor and capacitor?
Inductor and capacitors in LC circuit, that creates a sine wave. I made a lecture on that, but it's not even on the exam.
Because that's not on the exam.
It's not
Okay.
Thank God, I wanted to watch that.
Okay, right hand rule. F equals QED.
This is uniform now?
Yeah.
Sure, erase
Which way do we point our fingers for this right hand rule?
Erase everything.
Oh, right handle.
Yeah. That's okay.
No.
It's like
The
this,
1
it's like
minus
this.
e to the power negative t tau over tau is the charge in a capacitor, right?
Or like this.
This is the general equation.
Charging a capacitor?
Yeah, charging a capacitor or voltage across a capacitor.
Got your magnetic field.
So we have B is pointer. B is middle. F is thumb.
Yeah, I remember. I remember.
Alright,
right
good.
handle. I'm crazy.
Magnetic field curls around your thumb.
Yep.
I think everyone knows that one.
Dude, I have a sick drawing of that in my notebook.
Nice.
But the phone is F. What's F?
Ferromagnets versus paramagnets.
F equals VD. Which ones means what again?
V is velocity. D is magnetic field.
But the velocity of the current, right?
Charge. Velocity of the moving charge.
Yeah,
Just
yes,
the
that's like,
experience.
can you just call it the V's the current?
Yeah, right. So also force equals I-L cross B, where L is the length of the wire vector, B is the field. So this is experienced wire. Okay. Paramagnets are temporary. This is vocabulary will definitely be on the MCQ. Ferromagnets are permanent.
Bro, I knew it.
Good.
Bro, like what? This is... Maybe I'm not cooked for this test.
Yeah, moving on. Biot-Savart's law. dB is equal to. This is when we do downfold against. Just U naught I cross. No, wait, what? Oh. It's R hat cross. No. Okay. U naught I D L cross R vector over 4 pi r squared. You guys remember Biot-Savart's law?
Yes, I do.
The differential over here, we have
Oh yeah, that's the one for the wire that goes woo, and then you.
And you guys haven't practiced a lot of your vector integrals. You guys need to know how to do vector integrals. So
Oh, I know.
it's not that hard. You just take the integral of all the components, but still.
Yeah.
Okay. We have integral b cross dl equals mu and I. Now that we also know, we add mu epsilon derivative of electric flux with respect to time. You only need to use some of these. Sometimes you don't need to use both of them all the time.
And you need mu and I for the current,
Yeah.
and then the mu epsilon
For
delta.
changing flux. Yeah.
And then flux would change if.
You have like some
It's
charge
a-
getting closer but not actually going through, for example. I don't really know when that would be. It would be a very specific problem to say that. Like you had you're in some like big electron machine with changing magnetic electric flux. I don't know.
That's weird.
Okay, for a solenoid. I'm not sure you guys ever saw the lecture about solenoids.
Oh, I saw it.
Nathan, do you know this one?
To calculate the electric field in a solenoid.
It's.
So into the screen it's going like this, so it's like that. And that means the magnetic field will point this way. So magnetic field points this way through a curled wire. When the current is going, the I is going up this way and it's coming out this way.
Yeah.
And if you draw an ampere loop around here, we get B is equal to mu
and
turn density I. So N is equal to big N over L. And this is, wait, yeah. For an infinitely long wire, we have the electric field around it is just going to be mu big N I over 2 pi r. Which is actually the same as the solenoid equation, sort of. No, not really.
Kinda is if you like squint.
Just that's pretty much it, man. Lenz's law, if you guys know how to apply Lenz's law, you're pretty much good with the entirety of the other thing. Induced current is equal to negative N d flux B dt, but pretty much you can just get rid of all that. Which is
There's one loop.
it's almost
Oh
just one
yeah.
loop. If there's multiple loops, make sure you keep the M in there. Okay.
There's actually a question on there from you that uses that. How is one of that?
So yeah, expanding loop, shrinking loop, rotating loop, change in magnetic flux or field in the loop. But we have, remember, integral of magnetic field dot dA equals 0, but the integral of magnetic field dot dA without it being closed does not necessarily be equal to 0. It is just piercing through a surface. And finally, we have inductors. Inductance is L, it's measured in henries, and then induced EMF, or the potential difference across inductor, is equal to L d I dt. The derivative of current this time, not just the derivative of charge. That would be the second derivative of charge. And then using the solenoid derivation, we have L of a solenoid is going to be equal to N squared L mu times area. And I'm not sure if that's on the equation. So. time constant of an LR circuit is L over R, not LR. And then here it's going to be actually current, that's the thing, that's approaching the thing. And the derivative of that is voltage, which is going down. So in the last one, voltage went up and current went down. On this one, current goes up and voltage goes down, which is weird. Because here, voltage is the derivative of current, but
yeah.
here, current's the derivative of, charge, which is related to voltage.
Oh yeah.
Potential energy of an inductor is equal to 1/2 Li squared. And we had Maxwell's equations. And yeah, that's it. That's all.
Oh, true.